All right, welcome. Today is Monday, April 27th, nearing the end of April and on to May. Today we'll continue our review series, now going into the E&M test. So we'll start off with the electrostatics unit, then tomorrow we have the circuit stuff. It's basically, capacitors and all that. And then we'll be done with our review series. Remember, Wednesdays we don't have anything new on Wednesdays. Wednesdays is meeting days for us, and I guess if you run into questions, you can always email. But you do have tons of work to do. Your video project, your my AP homework for mechanics is due, right? So you have tons to do still, so make sure you get on that in preparation, of course, for our test. What about the RC? We'll talk about the RC cars after the AP test. All right, so let's get to it. Starting with the question we left off with the roller coaster in loop-de-loop, where you're rolling without slipping. Only one person solved it, and that was Huey. Good job, Huey, wherever you are. I was hoping we get more people to solve it. Hey, there he is, without slipping. He's been lurking all this time. He never once said anything in chat, but he's always there. Good job, Huey. So of course, the thing that changed was that the initial gravitational potential energy is now in three parts: Peg 2 and Kakarot. Believe it or not, this question was on last year's mechanics test, or at least like one part of an FRQ. So we have Peg, the original Peg, turning into Peg plus Kakarot, so MGH is equal to mg. The second one is 2r high, or the diameter worth of height, plus Kakarot. Kakarot is 1/2 mv squared. Now your center of mass, v, represents the speed of the center of mass, of course. So your center of mass still has to go rad gur, or square root gur, but just that some of the potential energy is also converted into the rotation of 1/2 I omega squared. And I for your marble is 2/5 mr squared. And then times omega squared, and of course v over r is omega. And so we get root gur over r squared. And then you can see how all the masses cancel, all the g's, the gravitational constant cancels, because this is going to square and all that stuff. So one of the r's cancels here. Oh, sorry. Yeah. And you end up with h is equal to 27 over 10, or 2.7 r. All right, easy stuff, easy stuff. So anyway, electrostatics. Of course, I always turn to the little chart that we had, because it does involve a lot of stuff. The basic stuff is all AP1 stuff. So the AP1 stuff is this chart, where force, or magnitude of it, is equal to K Q Q2 over r squared. E, which is the electric field, is equal to k q over r squared. And of course, this is for point-like charges. Point-like charges. Then we have potential energy, which is k q over single r, and then we have electric potential, not voltage, but potential. Electric potential. The difference of potentials is voltage. This is P, and this is self-explanatory. K single q over single r. Of course, both of these can be positive or negative. Scalar can be plus or minus. And these two are vectors. Right? Newtons per Coulomb. Chat, what is the other unit that you can use for electric field? Ooh. What is the other unit while I write the other stuff? This is joules. Oh, joules. Is it volts? V volts. Peterson gets it. Volts per meter. Volts per meter. Yeah, that's straight from your VED equation. VED. So we can do integral of FDR to get work. Here F equals QE. P is equal to charge times voltage. I should do delta here. So delta PE equals delta P. Alex isn't wrong. What does he have? Kilogram meters cubed per second squared Coulomb. Ugh. All right. And the new one is this thing. And how do we relate E and V? E and V. We get no. VED is only good for where E is. There you go. Where E is constant. So VED is only for where E is constant. And this is delta V, technically. And we use this in a parallel plate capacitor or a uniform electric field. Use for parallel plate capacitor. And the general equation would be E is equal to negative dV dx. Nope, not velocity, it's potential. Gradient of the potential. How do you get direction from change in scalar? What do you... Oh. Yeah, E goes from... well, E goes from... Let's see. Let's say you have a positive charge. And of course, from a positive charge, the electric field points away from it, right? But the voltage, the equal potential lines, are based on radius. And so the closer you are, the higher the voltage is. And as you go outwards, the lower the voltage. So you go from high to low. Oops. High to low potential. Well, a parallel plate capacitor has a positive and negative plate. Yes. So it goes from the positive plate to the negative plate. So it's nice and uniform. What happened? Minus? Mystery Wizard says minus? What do you mean minus? Oh, it's supposed to be a face. Minus underscore minus, but he did it in 2 lines. That's an L. That's the integral of a bunch of DLs, that's for sure. That'll be our new diss, right? If someone messes up, yeah, you just integrated a bunch of DLs there, buddy. This may be a stupid question, but potential around an electron is negative, right? Yeah, so around negative charges, you have negative potential. Negative volts. Right, so notice how over here I said scalar, but can be plus or minus. The plus or minus will be based on the charges. Okay. So that is also true for our potential energy. So if you have plus and plus, 2 positive charges, okay, notice how you have positive potential energy. And if you have minus and minus, again, you're going to have positive potential energy in your system. Now, if you have plus and minus, you're going to have negative potential. Similar to how you have two masses out in space and you have negative gravitational potential energy. Just recall that at infinite distance, you have 0 potential, and then as you get closer, you're doing negative work. So the same thing happens with attractive forces. So in the electrostatics world, to have an attractive force, you would need 1 positive, 1 negative, and therefore the interaction is attractive. Therefore, you have 0 potential energy at infinite distance. And as you get closer, as you bring the 2 opposite charges closer together, you're doing negative work. All right. So again, it can be plus or minus. So for potential energy and for V, you can directly plug in the signs. Whereas for E, technically, these are all absolute values. The formula will just tell you the magnitude. You have to figure out the direction on your own. It's away from plus and towards minus. Now, of course, these are vectors, so you have to do vector sum and all that stuff, all the AP1 stuff. All right, now let's get to the new stuff. You should know how polarization works. You have all that stuff in your notes. Polarization, so look it up. Polarization. Charging by induction, which is also important, so look that up. Remember, it's a 4-step process. Charging by induction, so without touching. Check the 4-step process. 4-step process. Neutralization. Charges. You don't actually destroy the charges; they're still there, Neutralization just means you're forming neutral atoms in that they have equal amounts of positive and negative. Okay, and it doesn't have to be 100% neutralization. You can have partial neutralization. So if you have two systems forming neutral atoms, or partial neutral, or partial. So if you have two charged objects, these two balls here, plus 3, minus 3, no, minus 2, any connected via conductive wire. Okay, these will neutralize. The system itself has plus 1 Q. And recall that if you break it, then it'll split up into half and half. Now Q is a variable. Q is a variable. Therefore, you can split up Q into fractions. However, E is not a variable. E, which is the quantized or the smallest amount, is equal to 1.6 times 10 to the negative 19 coulombs. So if you're left with one E, remember you can't split the E into half and half. It's just 50% of the time it'll go into one ball, and then 50% of the time it'll go to the other ball. Okay, so pay attention. Remember, the charges are quantized. To recall the pennies, I'm sure you have PTSD from the penny thing. But there has to be discrete amounts, whole numbers. Vector stuff. I'm going to skip over vector stuff. I'm sure you know how to add vectors. Make sure you break down into components. All right, now let's get to the actual fun stuff. We used lambda for densities again. So these are charge densities. Lambda is still charge per length. So this is linear charge density. Chat, what do we use for surface density? Surface charge density. Eta is correct. Eta. Charge per area. And volumetric charge density is theoretically possible. So rho, we're still using rho. We just have to you have to understand it contextually. So are they talking about volumetric mass density, or are they talking about volumetric charge density? Q per volume. Okay, but you know it's not as common. Absolutely, it's not as common. Typically, if you're using conductive material, the electrons, or I should say charges, would prefer to spread out across the surface, as it has the most amount of surface area, so they can be as far away from each other as possible. Right. But as you load it up, as you put more and more charges, it'll continue to get on there. Yeah. So it will penetrate if it needs to. All right. Know how to do the integrals for electric fields. So we did simple ones like rod. So integrals. For electric field E. So do rod. Do it by yourself, or take a look at your notes. You have them there. So electric field somewhere near some distance, some x distance away from our charged rod. And of course, each infinitesimal amount of 3D rod, no, not 3D, very thin long rod of length L. Okay, so you need to do it with L, and then consider the extreme cases where L approaches infinity. So see what happens when you have a near infinite rod. Right. So each infinitesimal dq will apply its own electric field. So this dotted line represents the distance, the line of action, but the actual electric field would be along the line, but starting from the dot itself. So that's the electric field. This is D electric field, DE. We'll call it DE1. And then the next one and the next one. So there, of course, is another one up here along the line of action. So you draw a line that connects the 2 points, and then along that line, starting from the dot, go away in that direction. It's away because it's positive, and then you start adding up all the DEs, essentially getting, you know, a value that is to the right. This is so E, of course, is equal to EX in this case, as EY is 0 due to symmetry. Assuming you're in the middle, right? Assuming you're in the middle. Now, if your rod is infinitely long, then where you are doesn't really matter. So you could be slightly off. You could be slightly off if your rod is long enough, if it's infinitely long. And then we can start using Gauss's law. How do you do this stuff? Well, start with your density. So set up your density functions. Lambda is equal to Q over L. Okay, then from there you figure out what dq should be. So each infinitesimal amount of charge, dq, should be equal to lambda, the constant density function, which is a constant, times however much you want to integrate. So in this case, since it's already in the y-axis, why not just use dy? So we're going to place our rod along the y-axis at the origin here. And so each infinitesimal amount is a dy amount. Okay. What are our bounds? Well, we're going from negative L over 2 to positive L over 2. Right? And then from there, it's just plugging it into the electric field equation and just integrating. So the electric field should be equal to kq over r squared, right? Now we're going to use this general formula. We'll convert it into our specific equation. So our net electric field is the sum of all the DEs, we'll say DEX. And this part is important to establish in that, yeah, it's dl is dy. Yep. This part is important to establish because you can only integrate vectors if all the vectors point in the same direction. So these are the critical things that you may need to know, especially going into problems where you have to discuss, write, justify. Right? I'm very confident that the AP will change the type of questions that they've been asking on our tests, so less calculation based, more explanation based. So we can only add vectors if they, I shouldn't say add vectors. Now, of course, you can add vectors. If they point in different directions. I should say we can only integrate if the vectors point in the same direction. Okay, so what are we integrating? What are we integrating? I'm running out of space, so let me move this. We're integrating all the x component of e's, so that would be k. And it's okay to use k, especially when you're doing these types of integrals. The only time you want to change k is when you start using Gauss's law. Q is actually dq over r squared, and we have to figure out the function for r squared. Times cosine of theta, of course. And we have to figure out what the function is for cosine. Yeah. All right, so r is the distance, and so if you use a little right triangle trigonometry, r is the distance from your dq to your point. dq to the point. Uh-oh, baby's crying. BRB. All right. So r is the distance. Now we can use trigonometry and see that r is equal to square root of y squared plus x squared. All right. And then cosine is opposite over, sorry, adjacent over hypotenuse. So we can rewrite the cosine function as well. So the opposite, or sorry, I keep saying opposite, adjacent is x, and then the hypotenuse is r. And then you replace and all that stuff. Now, can you do it with trig? Technically, yes, you can. Maybe it's, let's see. So you get kx lambda dq over y squared plus x squared to the 3/2, like so, integral. Oh, I didn't put, oh, it's not dq. I substituted dq, it's dy. There we go. From negative L over 2 to L over 2. And then do some tricks up. Let's see, y is equal to x tan theta or something like that. And then, I don't know, let's take a derivative real quick. dy must be, tangent is secant squared, so x secant squared theta d theta. And then substitute and blah, blah, blah. All right. You could substitute, do the integral, and then resub so you can get your bounds the way it is, right? So you could do that way. But essentially you get integral of cosine or something like that, and then sine. So you get sine of theta, and sine of theta is opposite over hypotenuse. So we get y over square root of y squared plus x squared from negative L over 2 to L over 2. And on the outside you'll get k lambda over x. Right? If you have time, could you go over how a conductor reacts to different charges on the inside and outside? Yeah. Okay, so anyway, so do the rod. So that's how we did the rod. Okay, you should be able to do thin little rings. So do this one as an exercise. So looped wire, if you will. Looped, I shouldn't say wire, I should say looped conductive string or something. But yeah, that's when you do Gauss. So do E from thin ring. So it's still lambda. We'll say it's z distance away. And then after you do that, then do a disk. A thin disk. Okay. And I mean, technically we already derived all these, so do it for practice so you know how to apply the integrals. What's next? Dipoles. Dipoles are highly unlikely. I'm going to skip over dipoles. Torben, can you answer? What? What just happened? You're asking Mark to check his emails? All right. Electric flux. All right. So I mean, we're getting to Gauss. So don't worry. As soon as Mr. Z says, "I'm going to skip dipoles," a question appears on the AP test. Well, I'm skipping dipoles because I mean it's in your notes and it's pretty SBO and it's not worth spending time. Yeah, so I mean there's a little torque equation, right? Dipole moment cross E. So fine. For dipoles, you have torque is equal to the dipole moment cross the electric field. And just remember, the dipole moment in physics is in the opposite direction to how you learned it in chemistry for some strange reason. And so if this is a minus charge and this is an equal amount of, to have a dipole, it has to be equal charges but opposite. So it's like a dumbbell. Yeah, exactly. Dipole FRQ is very unlikely. That's why. But anyway, I mean, here it is. So equal charges but opposite, equal in magnitude, opposite in sign. And so we have theta here. And so the dipole moment, the p vector, which is not momentum, this is dipole moment vector. Dipole moment vector. The dipole moment vector, I'll use green. Green. Dipole moment vector is that away. Truck outside. What? All right, whatever. No, it's sparklets. Dropping off water. All right, so anyway, those are dipole moments. Let's get to the actual question that's probably going to be on the test. Starting with electric flux. The electric flux is equal to E dot dA. Oh, sorry, I shouldn't say E dot dA, but E times A, or the dot product of E and A. It's got to be everything on dipoles. Yeah, every single. Why wouldn't you say the country? All right, electric flux. So if I have charge, we know that the electric field radiates, from plus to minus, and so if there is a certain amount that we can encapsulate in a certain region, so let's zoom in. If I zoom in, they're only slightly deflected, and so we use a little window to capture this electric field inside this area A. Recall that the vector itself would be orthogonal. This is the area vector. The area vector is 90 degrees. Is 90 degrees to the surface of your plane. So ISBO stuff. Here we go. Now, from here we can capture all of the electric field. So let's say I have a charge, and then we know the electric field is coming out, and we're going to use tiny little amounts of area to capture every single ray, right? And we encapsulate it. The amount of area I would need is the surface area. Surface area of a sphere is let's do it this way. Area of a sphere is 4 pi r squared, right? So if I integrate all of the electric flux, what I end up getting is all of the electric field times every single dA. Okay. Now we are strategically placing all of these areas, these little tiny dAs, so that the electric field goes parallel to the A vector. Or in other words, the electric field is always perpendicular to the surface of each little area. So it's perpendicular to the surface, it's parallel to the actual vector, such that I get 100% flux every time. Right? If the electric field was not parallel to the A vector, so if you have electric field going diagonally, then you have to do the actual dot product. So flux would be equal to A, oops, I should do E, not A, E times A times cosine of theta, the area, the angle between E and A. All right, so we end up with this. Then from here, it's just trying to use trying to use some calculus here. Let's see. We can get all of the area. Let's see. E is equal to K times Q normally over R squared. Okay, and this is where the this is where you start using the other form of K. Chat, help me out. What is K also equal to? Chat seems pretty quiet today. Sword Hero is not here. That's probably why. Recall that K is equal to 1 over 4 pi epsilon naught. So 1 over 4 pi epsilon naught. Okay. So this obviously this derivation was a little bit more challenging because we ended up doing double integrals from 0 to 2 pi, because this is an area integral, so it's actually a double integral because you have to integrate two different axes at the same time. 0 to pi. Okay, and then you have Q over 4 pi epsilon naught over R squared, and then dA, the dA turns into, I'll use pink, dA turns into, in double integral form, we get R squared sine theta d theta d phi. Yeah, it is polar. Now, as far as the APC test is concerned, this derivation is not necessary. Of course, you can do it. Remember, when you do it, just do it one at a time. Cancel stuff out. Pew, pew, right? Take out any constants. Q is a constant. Pi is a constant. Epsilon naught is constant. 4 is a constant. And then do one thing at a time. So this would be, so you do here, let me use blue. So you do one integral at a time. You do the inner integral, which is integral from 0 to pi of sine of theta d theta. Do that first. Once you do that, then you can do the second set, the outer integral. So you just do it one at a time, but factor out all the constants. And after doing all that, you end up with phi is equal to Q over epsilon naught. Q over epsilon naught. Okay, and this is what we put together. This is where we put together what we know, and that is the flux is equal to Q enclosed over epsilon naught, so whatever's inside of our surface, and then we set that equal to the closed loop integral of E dot dA. Okay, and this is our Maxwell equation number 1, or Gauss's law. So now we can start using shapes. So if you have point-like particle, so point charge, use sphere. Okay. If you have a rod, what do you do? What's the Gaussian surface that you want to use? Cylinder, yes. So if you have a dot, then encapsulate that dot with a sphere. If you have a rod, then what you do is you encapsulate the entire rod using a cylinder. Okay. So what is the radius? The radius is going to be based on where you want to find your electric field. Okay, so if you want to find it at this point, then you create a sphere that has a radius based on the distance from your charge to where your point in question is, right? So if you want to find the electric field here, then you extend the sphere out and make an even bigger bubble. Okay, what Gauss's law tells us is that, what this law tells us is that the value is the same along the surface of your imaginary Gaussian surface here. The value is all the same due to symmetry. Okay, same thing with this rod. Again, it has to be a very long rod. Because it's very long, we can ignore the top side and the bottom circle, the top circle and the bottom circle of the cylinder, and we can just focus on this green portion here. This. Okay, so when you cut it open, what you get, it's almost like a paper towel, right? Or an aluminum can, and you slice it open. You basically get a rectangle. The height of it is whatever the length of your rod is. Right? And based on how far away you are from the rod, or the radius of your cylinder, that will determine the width. And so that's the circumference. Now using Gauss's law, it's very simple. If I encapsulate this thing, we get integral of E dot dA is equal to Q enclosed over epsilon naught. And then you factor out the E because the E is constant. Then integral of dA is Q enclosed over epsilon naught. Now integral of dA is the area of your Gaussian cylinder without the top and bottom circles, which is just 2 pi r L. And so therefore the electric field must be Q enclosed divided by 2 pi r L over epsilon naught. And you can also rewrite it noting that you have Q divided by L. This is charge per length. What is charge per length? Well, that's linear charge density, lambda. Can you ever have a Gaussian surface with a charge on the surface? No, that defeats the purpose of creating this Gaussian surface. When you do your Gaussian surface, it is around a particular charge. Now you can have multiple charges, and then for each one you can do its own Gaussian surface. So it is possible that it may look like your Gaussian surface for one is touching another charge or something, but what you're doing is you're using superposition principle where you are mixing different things together. So it's not that there's a charge on a Gaussian surface. The Gaussian surface is an imaginary surface. It doesn't have anything, right? It's just some distance away from your charge in question. So typically in APC, all you're doing is you may do superposition, and we'll talk about those things when we do hollow spheres and stuff. All right. let's see. So charges. So let's do those things. Let's see. So let's say you have two. Yeah, very good. Ah, interesting. So we have this hollow spherical shell. No, then, okay, so if you have a rod and somehow you want to know the electric field at a point, but on that point you have a charged particle. Now, if you are at a point that has a charged particle, that charged particle obviously is going to dominate, and then you have infinite electric field. Whoa, my infinity turned into a hexagon. You have infinite electric field if you're like directly at the inside of a charge. If you're inside a charge, it's kind of, meaningless to talk about electric field at that point. You're inside. Yeah, then you can try to use superposition. Yeah. So if you're over here, then you can try to use superposition. So it's the Gaussian. It's the rod plus, if this is green, let's see, it's green. Rod plus sphere. I mean, if you have it's just E is still a vector, so you're just you're adding the vectors, and because and if this was positive, of course you would add the two vectors, right? Green would point away, blue would point away, and if this was minus, you would subtract them, and etc. All right, so here we have a thick shelled one of radius A, radius B, like so. Actually, we're running out of time, but I'll just finish off here. We'll continue on with, because we have more stuff to do on electrostatics, so we'll continue on with electrostatics tomorrow, and then Thursday and Friday we'll do circuits and other stuff. So we have E1 on the inside where it's hollow, E2 in between, and then E3 outside, right? For A, E1 inside, well, E1 inside is equal to the closed loop integral of E dot dA, but when you enclose your sphere, you'll see that you encapsulated nothing. And therefore you have nothing, right? This is the shell theorem, Newton's shell theorem, and you can do it where all the electric fields cancel each other out. Part B, E2 on the inside. This is where it's interesting. Okay. Again, use Gauss's law. So you are encapsulating a certain sphere of charges based on your radius as your radius changes from A to B. Right. So what do? Well, we start off with the same formula, E dot dA. But what we need is a new function for Q enclosed. Okay, so we turn to density functions. Rho is equal to the volumetric charge density, Q enclosed, divided by the volume V. And so we have Q enclosed, the total charge, divided by 4/3 pi r cubed, where r is changing. Okay, so we start the setup the same way. E, you factor it out, and then you have the integral of dA, which is your whatever your area is. is equal to integral from A to R. We don't do A to B. We do A to R as R approaches B, and we'll figure out what that is because we want it as a function of R first. So your lower bound is A, that's for sure, but your upper bound is R, a variable. Q enclosed is, so let's see, dq must be equal to 4 pi, oops, this is the surface area, 4 pi r squared times dr. dr is the tiny amount of radius that you're going to extend out. So if I zoom in, dr is going to be the tiny amount that you're going to extend out to increase, to make it like a shell, a thin little shell. So you get dr, and of course times rho. I forgot rho. Here's rho. So this is volume, right? Let's take a look. This is the density, rho. The 4 pi r squared is the area. So area times one more dimension, dr, gives you volume. Gives you volume. So you get 4 pi r squared dr times rho. Here, I'll write rho in the front. Divided by epsilon naught from A to R. Okay, finish it off. Part C, E3 on the outside. Now, once you're outside, then you're encapsulating the entire Q. You're encapsulating the entire Q. If we start off with Gauss's law, E dot dA is equal to Q enclosed over epsilon naught. Your entire encapsulation is the total charge Q. So Q enclosed, whatever it is, divided by epsilon naught is equal to E times dA. The integral of dA is the surface area. So however far away you are, which happens to be 4 pi r squared, and therefore on the outside you have 1 over 4 pi r squared times Q over epsilon naught. Okay, and if I were to rewrite this, we get Q times 4 pi epsilon naught r squared, and we know that 1 over 4 pi epsilon naught is K. Oh look, it's Coulomb's constant, and voila. On the outside, even though you have a shell, on the outside it's like a point-like particle. So this is why we can do the same thing with gravity. Of course on the inside of the Earth it's different, but on the outside the entire Earth is like a point-like particle, point-like mass. And then we can find the gravity some r distance away. Luckily for you guys, gravity is not on the mechanics test. All right, so thanks for tuning in. We'll go over more Gauss's law stuff tomorrow. I'll see you next time.